For the tutorial today, I provided essentially two Jupyter notebooks, one of which has sort of open parts and places to fill in if you would like to take some time during the tutorial to actually code in some stuff and follow along. And I'll sort of give people a few minutes at certain points to just be, have some time to essentially try your hand at coding some of this up yourself. And I've also uploaded a completed version just in case it's more helpful to you to just follow along with sort of examples that I've already filled in. So as Lauren mentioned, I'm doing the introduction to Bayesian Inference today. This sort of should be a nice, pretty back to basics preview of trying to understand the basics of statistical inference using linear regression. And linear regression is kind of this bread and butter example that comes up all the time in all these different statistical concepts and machine learning. And that's really because although it seems really simple to essentially just, how hard it can be to fit a line, it actually is kind of this really insightful exercise. It introduces a ton of different ideas into the problem. And so that's sort of what I'll be going through today. And so unfortunately, it doesn't look like I'm actually able to get the chat to pop up. Oh, there we go. Got it. And so hopefully this, should I zoom in a bit more? Does this look good? And so the basic idea behind linear regression is it provides this avenue into essentially thinking about what your objective is when trying to fit functions. So looking at, say, trying to find a loss and trying to minimize that loss or minimize the residuals. Trying to then go beyond that and sort of understand the basics of probabilities and define likelihoods. And then going beyond that to actually estimate parameters and do real inference. This is kind of the core of Bayesian inference and most statistical inference algorithms, is the difference between what a probability is and what actually inference is. Introducing the concept of priors, and then finally being able to take some of the results, visualize them a bit, and then trying to marginalize over the uncertainties when generating predictions. So to get started, essentially, we first need to look at some data. And so if you run sort of these initial set of cells, we're going to have a little basic script to generate some mock data. You're welcome to look through the details of how this actually works, but don't worry about them here because we're going to come back to them when we define a more formal model. So let's just grab some mock data and actually visualize what we're going to see here. And so this is what we're actually trying to fit a line to. And I try to generate this data to look a lot like what you might see either in your own projects or in the literature in astronomy, which is often you have quite large error bars, you have a lot of scatter, and you're sort of looking at this wondering like, okay, I see some evidence of like, a linear relation. I can kind of draw a line that goes through the center here, but maybe it's something a little flatter, maybe something a little steeper. It's kind of difficult to tell, what's the scatter? How would you quantify some type of correlation? It's not necessarily super obvious what exactly you'd be doing here. So the problem that we have is that we have essentially just want to define a really simple linear relationship, which is you want to just take this model that says, y equals mx plus b, which you've probably seen a billion times already. And we're going to make this model slowly more complicated as we're going to try and capture different features of the data. But just to start, I want to say that it's actually usually a perfectly reasonable thing to do to actually just take a look at the data and ask yourself, like, what would I fit by eye? If I was eyeballing a best fit, what type of results would I actually expect? This is often a procedure that's sort of jokingly referred to as Chi by eye, which is just eyeballing data and just seeing what looks like a reasonable fit to you. And so for anyone who wants to follow along, you can take just a minute or two to essentially plug in different values into this cell. Like let's say, a slope of 0.3, an intercept of 3, and just seeing, how that compares with the actual data set, and just play around with, what values do you think give you what looks like a pretty reasonable fit? And then after that, try and see, in addition to that, what you might consider to be some of the uncertainties on the fitted parameters. At what point would you say that this fit is no longer actually so good? and you actually would prefer to, and would you say that you don't really allow, say, slopes of, 2, for instance, to this data set? And the reason I want to start out with this is just to point out 2 things, is that first, it's actually pretty straightforward to achieve what you might consider to be like a reasonable looking fit, just by essentially using your eyes and kind of just fitting until things look okay. The second is that, surprisingly enough, even today, this type of chi-by-eye procedure is still used both to sort of get lines, but also to fit more complex functions. This is something that's come up a lot, for example, when trying to model populations of stars, where for many years, for instance, fitting isochrones or fitting other models was often entirely done by eye, since it was very difficult to write down, in many cases, what actually a good fit meant. And so this procedure that you're doing here might feel pretty ad hoc, and it is. And so we're going to compare later in the notebook how well doing something more rigorous and more quantitative is to this very simple approach. So hopefully, while I've just been sort of looking at some examples, I'll just sort of go through and plot up some of my guesses here. So just sort of based on playing around with this, I think that probably something like a slope of maybe 0.4, 0.5 seems like a reasonable fit to the data with an intercept of 3.3. The reasoning behind this is just that, with a line that looks like this, you essentially have something like maybe half or so of the data points above the line and the other half below the line. And that seems like a reasonable place to start with kind of eyeballing a fit. And this kind of seems to also go through sort of these last 2 points here on the end and also some of the points here on this other end. So this seems like at least a reasonable place to start. So one thing that you should probably think of immediately is that, while actually constructing this fit like this, internally in your head, you've actually done quite a bit of sort of mental math to characterize why this fit is good. And it's now time to sort of take apart some of those assumptions and see if we can make things a little bit more rigorous. So the first step is something that comes up all the time in machine learning, which is we need to define some type of objective function. In this case, what we'll call a loss function, to actually determine how well this model actually is doing at predicting the data. And this isn't necessarily something that's so easy, but just to start, we can say probably we want a model that gives pretty good predictions. In other words, when we're looking at the difference between the predicted value from our line, this again is sort of like mx plus b, and we're comparing it to the actual value, we would like a model that actually gives you small errors on that prediction. And probably ones that give you smaller errors are ones that are better than ones that give you larger errors. And so we can consider just starting by looking at essentially the absolute value of this residual, the absolute value being important because we probably only care about the fact that the prediction being accurate in absolute sense, rather than we care about the sign of whether something is off or not. This helps to avoid us by essentially having models that give you something that looks sort of right around the mean, but where the positive and negatives kind of cancel out. So that's at least, one argument for why this type of ad hoc procedure might work. And, we can then just define a model where we take our parameters here and our data here, our different X and Y values. And all we just want to do is we just want to add up the total of magnitude of all the residuals raised to some power P. And P here is sort of an important tuning parameter in our model because a priori, it's not clear which one it should be. Sort of a default value in lots of applications is 2, essentially taking the residuals and squaring them. But you can imagine that you might just care about having, the absolute values or having p be larger or smaller. In general, this is kind of set between 1 and 2. And one thing that is clear is that by changing the power that you raise things to, you change how sensitive the fit is to various residuals. If you make it smaller than 2 and near 1, in particular less than 1, then what you're doing is you're going to sort of take all the residual values and you're going to sort of squeeze them to be closer to 1. And so you'll be less sensitive to essentially larger residual values. If you then instead have p greater than 1, in this case 2, then you're going to be very sensitive to large residuals because you're taking those values and squaring them. So you become, in that case, you care much more about getting points that are, say, maybe outliers or far away from the fit than points that are actually quite close to the fit. And so for this next example, essentially, all we really want to do is, there we go. We just want to do is essentially define a loss function. So I've sort of outlined the basic concept of one here, where we want to take this prediction, we want to generate some residuals and return some loss over most of this. This would again be hopefully pretty straightforward to those quite familiar with Python, and hopefully accessible to those who are still learning. So we want to define this loss function based on the inputs that we've provided here. And then given that, we want to see how the loss changes as we actually change, for example, the slope, or as we change the intercept. And so by just filling in these two values, we can then get a sense for how changing the loss actually changes quantitatively how good or bad our model seems to be behaving. So I'll just give sort of a minute or two for you to take your own shot at filling this out, and I'll start to fill in elements of this notebook as well. And again, if people have any sort of questions or comments or things that they would like to ask about, please either ask in the chat or any other avenue.
Josh, you talked about this a little bit, but what is or at least what kind of intuition do you use to choose P?
So usually for me, when looking at the data, what I really care about when choosing P is looking at whether there are a lot of outliers. In other words, when we're looking at the scatter, whether there are sort of one or a handful of points that are really, really far away from the main relationship that you might want to look at. And in those cases, you usually want to pick values of P that are less than 2 so that you become less sensitive to some of those really large outlying points. But in this case, given that most of these look pretty reliable, we can probably sort of stick with the default choice of P equals 2. But it's important to actually explore, for instance, how sensitive your fit actually is to some of these various properties and how that changes sort of how this loss function behaves. Because you might have particular constraints for your individual problem where you want your loss function to either be more or less sensitive to some of these outlying observations. Because sometimes those can be real signals. If your model can't get a good prediction to say 1 or 2 data points, that might be something that you really care about. Whereas in other cases, you might just care that your model kind of gives an aggregate, reasonable prediction to all of them.
Do you ever go above 2?
Going above 2 is unusual. That's usually the case where you really, really want to penalize outliers. So if you're going above 2, that means that you want your model to be extremely sensitive to predictions sort of on the edges.
I see. And sorry, one last question. I hear people refer to things as like the L2 norm and stuff like that. Is that related to this at all?
Yes. So the L2 norm is essentially just P equals 2. So often in machine learning, L2 norm comes up a lot, which is just the sort of standard Euclidean norm, like the x squared, y squared type of stuff. And then the other norm is often the L1 norm, or otherwise known as sort of the Manhattan distance, which is kind of just taking the actual absolute values. So you can think of it as just being, looking at whether you're adding up sort of squared points on a triangle. So if the distance between 2 points should be equal to sort of the hypotenuse, Or if you're saying the distance between 2 points is similar to driving around or walking, which is you actually have to walk, the x direction and the y direction.
I see.
So in this case, hopefully you all had a chance to explore a little bit what this kind of looks like. I'm just going to fill in some grid of values here. And so all this code block is doing is it's just computing the loss for a fixed slope, which is your best guess by I. So in this case, it'll be mine from earlier, changing the intercept around in this grid that I defined up here. Let's define this to be 2. And in this case, it's just doing the opposite, where we're going to keep the slope fixed and we're going to change the intercept. And so here's what we get when we're looking at sort of the loss for each of these different parameters. And so this hopefully kind of intuitively makes sense. Our loss is, at this point is kind of squared. And so we expect that, as we maybe change one parameter, it should look a little bit like a parabola. We're kind of, shifting these around. We're squaring all the residuals. So maybe it should kind of look like a squared function too. And the same is true for the intercept. And you can see just how quickly sort of the minimum value is kind of around here. And then the maximum value kind of here increases pretty rapidly as you sort of go away from the bottom. If we change things to say, maybe let's make p larger than 2, you can see that we're kind of getting, again, sort of this behavior that looks now like more of a quartic function. So it looks kind of like, x to the 4. And you'll notice the values here now on the y-axis are much, much larger. And so we have to really zoom in to see what the differences are right around sort of the minimum point here, now that things are so big. We can also decrease it to be smaller. Let's say we make it 1. And you'll notice now we kind of get this little absolute value shaped thing. So it looks a little bit more V-shaped and a little bit less parabola shaped. So hopefully all of these kind of make sense. And again, you'll notice on the y-axis, the actual absolute values of the loss have changed as well. And of course, if we make it even smaller than 1, you might notice, for instance, if we make it the square root. So now we're actually saying that we want to penalize sort of less and less the further away that, or at least to a lesser extent, as points get really far away, we actually get things like this, where there now are as more complex behavior sort of near the bottom. Now you can get possible multiple best fit solutions. So these are all sort of important changes that you should take into account when thinking about this type of objective. For now, though, let's stick with P of 2. So one way of defining a best fit is that we want to just have a function with the smallest loss. So in other words, when we're making a prediction, we want just the residuals to be as small as possible. One way to do that in Python is just using this minimize function from the scipy.optimize package. So this is straightforward. So if we look at the documentation here, this is for a little bit of an old version, but the documentation is pretty similar. So if you want to use minimize to actually find the smallest value of the function, it looks like we just need to pass in 2 parameters. One is the function itself, and the other, if we zoom in here, is an initial guess. It's this x0 array. So we just need to pass in the number of variables. That's the initial guess to this function. And then it's going to use essentially various minimization techniques, which we can specify maybe with these additional constraints here, to actually find the value of the parameters, in this case, the slope and the intercept, that give you the smallest value for this function. So that seems like a reasonable place to start. So let's see if we can come up with an initial guess. And of course, the share screen window is right over where the, there it is, right over the tab. So you can feel free to fill in some of these as well. But for an initial guess, let's just start with our guess by I. So let's just say that it's, we want to start with our loss function that we defined earlier up here. And we just want to start with our by I guess and see if we get some results that change. So it looks like this terminated successfully. The results of minimize sort of print out in this little results dictionary. So you can see it has a bunch of different things. It tells you the basic status, a bunch of different times it had to evaluate the function. And some of these we'll actually come back to a bit later. The two things we care about is first that it gives you a function value. So it tells you here's what the loss is for the best fit points. And the second is that it actually also gives you the best fit values as well. So here is now the new slope and the new intercept they give you correspond to this particular value of the loss. So if we plot those out, we can compare that to our original result. That's sort of shown here. So we can see that in my case, when I was fitting by eye, I kind of got this red line. And now when we're sort of computing this objective function, we're just looking at the differences between the data points in black and the residuals from this line. It says actually the blue line is the best fit. And to my eye, these are actually pretty similar. So I'd say within sort of the uncertainties that I would sort of have anticipated, the blue line and the red line are pretty close to each other. So I could say that the sort of by eye fitting is not too bad here. But it's good to actually quantify some of this improvement.
Yeah, your card by eye was much better than mine.
So at least in this case, it looks reasonable. But it's true that the Chi by eye can often give you results that can change dramatically. So if we want to quantify, how much better we've done in each case, let's just actually compute what the loss is for both the initial one, and then maybe what the loss is for the new set of points, which in this notebook I just called sort of M2 and B2. So okay, so the difference is, at least in my case, is that sort of the initial fit had a loss of about sort of 24.14, and the second is more like 22.95. So the difference is roughly, a factor of 1. So if we're looking at, that means that if we're looking at the squared residuals, that means that this new fit essentially reduces the total amount of squared residuals by around 1, which is not a huge amount. So that's actually seems to agree with this intuition that these two fitted lines are actually quite quantitatively similar.
So Josh, when you were showing the loss and how it changed as you increased P, for larger P, you kind of got like a not a saddle, but like a much wider range of kind of similar loss values, right? Because it kind of flattens out in the bottom. Is there intuition there for because then it feels like you're maybe I could do a much better Chi by eye with higher P values, because there's kind of very similar, slopes and intercepts kind of have similar losses. Does that make sense?
So one thing that's a little misleading here is that the y-axis actually can change, is changing when you change the P values. So you'll notice in the original case, it was a few hundred, but now it's a few thousand.
I see.
So actually, if we wanted to really see what was going on, we'd have to zoom in to this region right around the bottom. And you'd find that actually with these larger P values, the loss values really shoot up a lot faster. So this is really looking at the wide scale behavior. But if you want to look at, if we're just trying to get the best fit, then it really matters, what's happening right next to 0. So similar in the case where if we make it, quite small, then the values on the y-axis here are sort of 4,000 or 7,000. And you'll notice that they sort of reduce quite a bit to just being like 100 or 140. So the total range of sort of residuals is changing a lot. This is always something to be on the lookout for. It's sort of the behavior right around here near the bottom that we sort of care about.
Do other folks have questions?
If not, hopefully this so far is kind of making sense. The next thing that we might want to do, though, is you'll notice that in this and lots of other data, right now this loss function just takes into account sort of how well the predictions do looking at the data points. But, we have all these beautiful error bars, and we would like to take some of that information into account, right? Intuitively, if we're looking at this and thinking about what the best fit line is, you probably want to, care more about points with small error bars like this one here, rather than points with really large error bars, like that are probably much more due to measurement noise. And so we'd like to take some of this information into account. So one way of doing that, and you can definitely think of your own methods to essentially change the loss function to allow for errors, is just to redefine exactly what a residual means. And so rather than thinking about just looking at essentially the numerator here, which is this, you know, delta y, you might want to say, well, let's just normalize this by the size of the error bar. So rather than looking at distance just in terms of how far away the prediction is from the fit, now let's define it in terms of how far away is the prediction from the fit in units of error, using this sigma I here. And this quantity is often called chi, which is known as the error normalized residual. So this just means that when we're, you know, say looking at this point here, rather than saying, oh, you know, the total distance is some value in y, we want to say, oh, this is, you know, maybe like 10% or 20% of the error bar. And if we do this for all the points, and this allows us to essentially downweight points with larger errors, where essentially we want to deviate, you know, in smaller units of error, and upweight points with smaller errors, where we now are further away from the truth. So with this, if we sort of see that if we stick with p equals 2, and you add up all these different new chi values, you get what's often called the Chi-Square Statistic. And this should hopefully sound familiar, in the sense that you see this all the time in the astronomical literature. Everyone talks about essentially the chi-square from their fit. Everyone wants to know what the best fit chi-square is. You can kind of see this is why they've defined it this way. So chi-square is just looking at the error normalized residuals and taking those values and squaring it. And so, you know, following exactly the same example as above. So we had some little code blocks here that we were looking at. You know, let's define a new chi-square function. Let's try and minimize it. Take some time to minimize this. And then we're going to take a look at the best fit results. And now we want to quantify, you know, how different is the results now that we've taken some of these error bars into account or not. So we can just take, you know, a couple minutes to just get a sense of, you know, code up this new function, see if we can minimize it, and then see what the new results look like compared to the original ones. So as before, I'll start filling in this notebook a little slowly and give people the time to essentially fill in their own copies if they find that useful.
Yeah, has everyone been able to find the notebooks on the Jupyter Hub? Is anyone having trouble finding the notebooks?
So in this case, as I'm just going through, I'm just defining as before, sort of we're going to define some residuals. Then to get the chi-square term, I'm just adding in the errors here, which we're passing into our function. And then now for a guess, at least for me, I'm just going to start with the best guess from before. So we're now going to take at least for me, I'm just going to use the best guess from the second part of the notebook. So hooray, it looks like it succeeded, at least in my case. And so we get some new best fit values for the parameters. And if I take those and plot them, now we see that, at least in this case, we're comparing the red was the original one for me. The blue was the one that we computed using our original loss function. And the purple is now the one that I am looking at using this chi-square. So now trying to take some of the uncertainties into account. And now at this point, you might notice the difference between the red and the blue is a lot larger than the blue and the purple. So this is really nice. It's saying that actually, you know, dealing with the uncertainties doesn't seem to change the results that much. That's really cool. So we can actually quantify what that improvement looks like just using the exact same method as before. So let's, for example, just compare the chi-square from the best fit model with those from the previous two cases. So these are the ones that I fit by I, and then also that I fit using the loss function. So we can say, oh, okay, look, like compared to the original one that I fit by I, this is a dramatic improvement. So now that we're looking at the error normalized results rather than just the actual residuals, you know, this isn't an improvement in loss of say like 1. This is now an improvement in sort of error normalized residuals by something on the order of 14. So that's now a pretty big improvement. But compared to that, the best fit result compared to the one that ignored the errors is actually quite similar. So the improvement in sort of the error normalized residual looks like it's less than 1. So this is one case where incorporating the errors changes the results a little bit. But I'd say statistically, if I, you know, by eye, when I'm looking at this, the blue and the purple look pretty similar to me. And so we're going to sort of keep going and quantify exactly what that means later on.
Josh, can you say a little bit more about the other outputs from scipy.minimize?
Yes. So we're going to go actually use this Hess inverse in a bit. But what scipy.minimize is telling you essentially from, in addition to just the best fit value it gets and the value it has, is it's executing a particular algorithm to try and find the smallest point, essentially using gradient descent. So that means essentially computing the change in the function at a given position. So computing the derivatives in both the m and b, and then trying to follow directions where that becomes smaller. And so that's sort of what some of these outputs are here. This Jacobian is sort of looking at the changes in the derivative, and you want it to find the maximum likelihood is kind of where that's around 0. So it's good that these are pretty small. So the best fit value is where the change in the derivative is 0. This tells you how many function evaluations it's done. So in this case, it's done 24. And then total amount of iterations in this algorithm is done. And then this NJ is the Jacobian. So how often it's tried to essentially get the derivative. And finally, this Hessian inverse is going to be right now is not actually such a useful quantity. But when we actually go through and define this function a little bit more properly, this will actually give us an estimate of the uncertainty. But for now, this quantity essentially is just garbage.
And I think it looks like you use just the default method, but do you ever play with the method that scipy.minimize uses to do the minimization?
Yes. So as you can see in the documentation, there actually are a lot of different methods that scipy.minimize can use here. And these can take advantage of various features of the function that you're trying to work with. So these two here, sort of Neldermead and Powell, are kind of the bread and butter that I often will resort to if the default method doesn't work, which I think is using essentially BFGS. And both of these essentially use numerical approaches to try and estimate the best fit using different strategies. Lots of these other methods work really well, but require you to provide either gradient information, so first derivatives, or in some cases, Hessian information, which requires second derivatives. So if you have functions where you know both of those things, these can be super efficient. But otherwise, some of these are a little, you can see details for all of these further down the documentation. They give wonderful overviews of all of them and link to individual pages. So for example, I often choose either Powell or Neldermead if I'm interested in doing something a little bit more robust, but often takes a little bit longer. So you'll notice the outputs here actually change a little bit because they're doing different things, but the same, the value of the function and the best fit value here look identical, which is nice.
Oh, interesting. Yeah, I saw the number of function evaluations go way up for that one.
Yeah, exactly. So Neldermead tends to require a lot more function evaluations because it's essentially using a slower but more robust algorithm. So at this point now, we're at sort of the part where we're going to transition into doing actual inference for the final sort of section of the notebook. And this is essentially just, at this point, we've mostly just been fitting things. We define this chi-square, but I would say all of these are kind of ad hoc. And so what I want to do now is make this, our model a little bit more complicated, which is to say we're not just going to fit a line. Probably when you look at this, you'll notice that, you know, the error bars here are large, but not as large as the scatter and the points. So you might think that there's some intrinsic error or scatter, and that we would like to estimate that too. And so maybe we can figure out what the intrinsic scatter is and add that into the observational uncertainty, and maybe that'll give us an even better fit, because now we can describe sort of all the scatter that's going on here. So I'm going to call that quantity S. And so now we want to estimate what this S is, as well as sort of just the slope M and then the intercept B. And so to start, it looks, the first thing I want that we might consider is let's try and modify our loss function to incorporate this new scatter. The problem is it's not clear like right away what exactly we would do. So one thing that I wrote down is maybe we can just kind of add it in like a constant. So we'll just kind of take every error bar and add in like a little floor and say, well, maybe this point has a measurement error of 0.2, but we know that like all points have a measurement error of 0.2, so the real measurement error should be 0.4, something like that. That seems like a reasonable place to start. And then maybe we can write down our chi-square model as before. But you'll notice that there's one immediate problem, which is that if we define our chi-square model to kind of just be the sum of all these individual things, then if we make S really big, then in all cases, we're going to be just decreasing chi, right? Because we're saying that, oh, if the error bars get larger and larger and larger, then the actual error normalized residuals will always get smaller. And so therefore, our chi-square, which is the sum of all these points, is also always going to get smaller. And so there's no penalty for us sort of just taking S and running it as large as we can get until it approaches infinity. So this is a bit of a problem. And whenever you end up in this place, this is often telling you one of two things. In this case, it's telling us that we don't really have a firm understanding of what's going on under the hood. We don't have a model for what our data is doing. And so we're reaching this point because we're trying to do these procedures using this ad hoc modification. And so often if you're trying to engage in modeling and you find that you're stuck in this particular problem, it's often good to just go back to your assumptions and say, do I actually have a model for what's happening here? Because that usually can tell me what type of guess I should be using. The second thing is you might say, well, that's not the end of the world. All I have to do is just maybe introduce some type of penalty term. So maybe I'll just have these two terms. So one is this is the chi-square. That depends on the data. And maybe the second one will be, I just don't want S to be really big, so I'm just going to add it in. So that way, if you make S really large, then it's going to sort of increase this. It'll increase the chi-square. And that means that there will be some point where decreasing the chi-square will balance out with increasing S. And here I just picked S squared because it kind of looks like it mirrors the chi-square. And so maybe this is an okay choice. But again, all of these are very, very arbitrary. And so the point here is whenever you reach this type of problem, then it's really telling you that you have to define a formal model. And so all models really start with trying to understand a data generating process. In other words, if you want to simulate data based on input set of parameters, how would we do so? The way I like to think about it is, if we go back to like the method that I'm using to generate mock data, what are actually all the step-by-step approaches that we're using in Python to generate that mock data? So I've left some space here for people to sort of fill in their own, their own way of writing some of this down. I'm just going to kind of sketch out what I think the main processes are that we really care about if we want to incorporate sort of the slope, the intercept, and this additional scatter. So I'm just going to use annotation to kind of write that down. So if we have sort of a given x, then if we knew the slope and the intercept, if we knew m and b, we can kind of generate some y value. So that seems straightforward. That's kind of what we're assuming by fitting a line. So that gives us the slope and the intercept. Now, if we want to add in the scatter, then maybe if we knew sort of what the scatter was, we could go from like this y value, and now we could get maybe some new value. Let's call it like, I don't know, y prime. So if we knew the scatter, then maybe we could take this original value from our line and generate some new value that we've scattered around a bit. And then finally, we have to consider, that we have these additional observational uncertainties. So maybe then if this value is here and we knew some sigma, then we could generate some additional, say maybe y double prime. And this is the thing that we're actually observing. And then it comes along with, this error bar that we have from sigma, and then some additional positions. So maybe something that like this kind of describes our data generating process. So to go from the actual underlying values to our observed data, we kind of need to know the slope of this so we get the line, some scatter so we can generate this intrinsic dispersion, and then some additional measurement uncertainties to generate the observed data. So maybe something along this line is a reasonable place to start. So this exercise is always really good when you're always trying to define a type of model. A huge portion of inference is just making sure that you can write down all this stuff and make sure that you understand all the assumptions. And so personally for me, I find that writing things down in this type of graphical way helps to clarify a lot of the modeling process. So because this tells us that we sort of have 3 different steps that we want to take into account: the sort of slope step, the scatter step, and then finally the measurement uncertainty step.
And Josh, which of those parameters are like per observation and which ones are kind of global to all the data?
So these 3 here would be global to all the data. So that would be the slope and the intercept, in this case, the scatter. So we're assuming that the scatter is going to be the same for all the data. And then this sigma, this is going to be individual for each point. So the measurement observational uncertainties for each point, and then also the particular, x positions and y positions, that will be different for each data point. So when we say scatter, the first thing we want to do now is quantify what exactly we mean. And error bars or scatter are really just telling us something about probabilities. In particular here, what we're saying is that the probability of observing some particular value, in this case, let's say y1, given some true value in some error bar, follows some probability density function, which is often called a PDF in most papers in literature. This is just saying essentially, if you have some intrinsic value and you have some error bar, what's the actual probability that you're observing the data point that you actually see? And these have 2 constraints. The first is that if you integrate this over all of the possible values you can observe, it should integrate to 1. That's just saying that your probabilities have to sum to 100%. The second is that often these have very particular shapes and sizes. Now in this case, when most people give error bars, what they're really saying is that the data that I have here follows a normal distribution, or often called a Gaussian distribution in astronomy. And that means that essentially the probability of observing any data point, I notice there's a small typo here, these sigma should have i's in them, is going to depend on 2 things. So it's going to depend on the squared distance between the true value and the observed value. And that's going to be normalized by essentially the squared error. And it's going to depend on this exponentially. So as you go further and further away, you're going to decline in sort of this, exponential power of. So as you move, say, 1 additional sigma away, your probability is going to decrease as sort of that squared to the e power. So this is telling, okay, so this is saying that, we're exponentially less likely to be, say, 1 or 2 or 3 standard deviations away. In addition, you'll notice that this normalization term is also important because we have to integrate to 1. That means that if we make the error bars bigger, or we make sigma bigger, then that means the actual maximum amplitude at any given point, or the maximum probability, also decreases, right? Because essentially you're saying that points can be more and more spread out. So that's just saying that if you have a very small error versus something that's very large, the actual error underneath these curves here all have to sum to 1. And so the maximum value at, say, this point here versus the maximum value at this point here are going to be different. So this does a couple things for us. So first, you'll notice that when we now write down our model, this term looks a lot like the chi-square term that we defined earlier. So it sort of naturally appears inside this exponent. And this connection between the Gaussian distribution or normal distribution and chi-square is fundamental to why that particular loss function works so well, is we're making this assumption about Gaussian errors. The second thing that this is so nice is that you can actually show, although it's beyond the scope of this particular notebook to prove it, that actually if you assume that the scatter S is also Gaussian, that actually you can kind of just add on the errors just like this. And so this tells us that we should actually be adding on these squared quantities rather than the quantities, you know, without the square. And so by writing down a formal model, we've accomplished essentially two things. One is that we can see our original model sort of reappearing inside the context of our formal model. So our loss function and our chi-square are actually in this expression. And we also have this really natural emergence of this penalty term. So if we make S much larger, we're going to decrease this amplitude. And a really nice way to actually add these parameters together. So you kind of see that by writing down a formal model, you get all of these different components all coming together and all these problems kind of naturally solve themselves. So
can I make a comment?
Mm-hmm.
For a sec, this is Dustin. This almost looks like the way these are coming in, like the way the chi-squareds get modified by the s-squareds. This would almost be like, it would look the same if the experimentalists had underestimated their error bars in a particular way, right?
Yes.
Do you want to? That's all.
Exactly. So this is also can easily be interpreted as either underestimating the errors by sort of a constant amount here. So this type of formulation is a very generic tool. And so in lots of cases when you're fitting observed data, being able to introduce something like this S is often really easy to do. And you can often find out pretty quickly whether the error bars that you're actually getting are probably either over or underestimated using some of these different tools. So to finally take all things together, we have to just go through a really quick round of probability, and then we're going to get to the end. And that's just saying that we have all of our data we're assuming are independent. So that just means that the probability of observing each of them is just going to be the product of observing each of them individually. So if you do some math and you write that down, that just means we're multiplying everything together. Often when we, instead of writing down things as products, we're going to write them down as sums, because taking logs of things and writing sums is a little easier. And you'll notice if we take the logarithm of this product of all these probabilities together and we do a little bit of math, you get this beautiful result. And you'll notice that this first quantity here, this looks just like the chi-square term that we were talking about earlier, except that now we have this really nice addition of this S. And the second is, you notice the second term here, and this is the penalty that I talked about earlier, just naturally emerges from actually looking at these probability distributions and trying to model the underlying statistics. So you naturally get this probability distribution just emerging, and so you get this penalty term. And so this tells us that actually we should be penalizing as we get larger values, but we're going to be penalizing by the log. So we're not going to just be doing S squared. So for those of you who are interested in modeling, you can definitely go through and write down some estimates. But all we want to do here is look at essentially the best fit likelihood. And so I'm just going to skip to sort of the notebook where I've done a little bit of that work already, because this starts to get a little bit more involved. And so what I've just done here is essentially written down this, more detailed likelihood out in functional form. So computing this chi-square term, this constant penalty, and then combine them together. And because we want to minimize this, we want to have a minimization routine. Because we want to find the best fit value, that's going to be the value with the maximum probability, or this is often known as the maximum likelihood estimate, or MLE. And so if we run our minimizer now on this new result, where we put in, say, our new guesses for the slope, the intercept, and a guess for the scatter, you'll see that not only does this converge, but it actually gives us an initial estimate for all of these different parameters, which now we can overplot and we can see is a little different from before. So you'll notice looking at this plot, the blue was the one where we ignored the errors. The chi-square is the one where we included the errors. And the orange, along with this shaded region, now is telling us both what the best fit slope is, which is kind of in between the two, but also an estimate of the scatter. And you'll notice that, this estimate of the scatter now looks pretty good compared to the actual scatter observed in the data. And so now, because we've added in this additional complexity to the model, not only have we slightly changed the best fit, but we're also able to estimate some of these real physical underlying processes in an interpretable way. So now we can actually go and say, we think that points follow this relationship. We think that the error bars or uncertainty has been underestimated by this amount because there's some intrinsic scatter going on. And so this is now an actual model for what actually we observe with our data.
I see. And so Josh, when you generated your data at the top, you actually included this term in your data generation.
Exactly. So way back in the beginning, I actually do include this this little intrinsic scatter term, and then I also include this uncertainty term as well. So we're now actually reproducing the processes by which I originally generated the data.
Cool.
So the last thing that I wanted to get into is that what we've talked about so far is essentially talking about the data. What we really care about is we care about the parameters of our model. And so what that means is that what we have written down so far is the probability of observing our data points given a best fit, line, a best fit scatter. So that's sort of written down here, where this line here indicates essentially conditioned on. So we're saying, given our model parameters, what's the probability of seeing the data? What we care about, though, is actually the reverse. We observe the data. What we want to know is, given the data, what's the probability of the model parameters? And so to get at that, we can exploit this little trick known as factorization of probability. And that's just the fact that the probability of two different things occurring is just essentially the probability of one thing occurring and then the probability of the thing occurring after that. So probability of both A and B is just the probability of B times the probability of A given that B has happened. And we can also flip the order around. And if we do a little bit of rearranging, we get something that looks like this. And if we just swap in, essentially replace A to be the data and the B to be our parameters, we get this functional form down here, which is known as Bayes' rule, which is that the probability of observing getting the parameters for a given data set is just going to be equal to the probability of seeing the data given the parameters times the probability of the parameters, what's that, and the probability of the data, what's that. And so this is the core of Bayesian inference here. This term here that we've talked about earlier, this is the likelihood that we've just been modeling. So this is everything we've been doing so far that describes how we think our data are generated and describes the baseline of our model. The second term now, the P of parameters term, this is known as the prior. This characterizes our knowledge about the parameters without having seen the data that we're looking at now. The term on the bottom is often known as the evidence or marginal likelihood. You'll notice that this doesn't depend on the parameters here, so this is going to be a constant. So most of the time, people just kind of ignore it. And this last term that we care about, this is what's known as the posterior, which is often discussed in Bayesian inference because it is sort of what you get post after looking at things prior. So that's often why it's known as the posterior after looking at the prior. So the thing about Bayesian inference, right, is if you look at it this way, all you just done is you're just essentially taking this, your likelihood, and you're adding on these additional terms, which you can think of like penalty terms, onto the data. And these priors are actually really, really important and a central component of Bayesian inference and something that you shouldn't overlook or consider to be annoying or a nuisance. This is really what makes it very powerful because these are telling us how much prior knowledge we're bringing in to any particular problem when we're doing estimation. And so in some cases, maybe we have very strong prior knowledge of what things look like. And so maybe the data can be a little messy and we can get some really nice results out. Or maybe in some case, we really don't know much at all and we really want to express sort of the level of our ignorance about the problem. But anyway, this prior term is something that can affect the results substantially and is something that definitely you need to think about. And it's not sort of a bug of trying to do inference this way. It's really a powerful feature that allows you to specify things that you already know and have that essentially change the estimates that you get out. So one possible prior that we could work on here is essentially introducing, is allowing our prior on our parameters to be Gaussian. And that means that in addition to this likelihood that we have here, so this again is our new modified likelihood. So it includes our slope and intercept, also includes the scatter. We can also add on, say like, okay, well, we can also have a penalty where we say that we think we know what the parameters should be. We have some, scatter for what we expect them to be. And maybe we just want to add that on so that we don't want the slope to, say, deviate too much from what we might assume that it is already. And we also have this constant, of course, which we can ignore. So this form here, this is the prior. And this will change depending on what sort of functional form that we pick. In this case, where I'm assuming that the priors on all these parameters are going to be Gaussian. And so that's what I do below, is essentially now I introduce these additional prior terms. And so what I'm assuming is that maybe from some prior experiments, I expect that the slope of the line should probably be maybe 1. The intercept should maybe be 3. Maybe the scatter should be something like 0.5. Maybe from past measurements or past experiments, I have some knowledge of this. And I have some uncertainty on that that I've written down here. That maybe, the slope can change by, sort of 0.25. The intercept might shift around by maybe 0.5. And then the final estimate might change by, for the scatter, might change by maybe 0.15. And if we write those down, we can sort of add those two terms together and run the same routine to actually compute this minimized result. And we can get an answer out. And you'll notice, for instance, that the answer here actually is a little different than in previous cases. And if we actually compare, say, what the gray curve looks like down here to our estimate before, you'll notice the gray curve and the orange curve do actually differ a tiny bit. And that difference is the impact of our prior on our analysis. It's actually changing our best fit parameters slightly in terms of what we're getting. And so again, in the original notebook, I've left lots of these different cells blank. So you can sort of go through and work on defining your own functions and maybe changing the priors if you want to change the priors around and see how it impacts the results. But one of the key things I want to end with that's always a core thing for Bayesian inference is that it's really important to do all this work so you can get uncertainties out. And that's because now you actually have some estimate of what the uncertainties are on the individual parameters. And so you'd like to use that to sort of be able to diagnose, how well can you constrain certain things like the slope and the intercept. Maybe that's very important if you're trying to, say, constrain a period luminosity relationship or something else. But it's also really important for visualizing some of these uncertainties. And so down here, I've plotted essentially what the starting values I've assumed are from the prior, which are shown in blue. And after running this analysis, what the uncertainties are estimated from our minimization algorithm shown here in red. This is both shown in 1D up here, and also the 2D distributions between each of the individual parameters here are shown down below. You can see, for instance, that the uncertainties in B and the slope and intercept are very correlated, whereas it's not so correlated in some of these other parameters. And being able to visualize some of these allows us to say, for instance, that maybe our prior on the slope and the intercept was not such a good guess because the actual data seems to be suggesting that it's a little different than our sort of prior beliefs. So that's sort of the end of this sort of starting tutorial. There also are some additional sort of stretch goals in a sense that if you want to actually take these uncertainties and visualize what they look like on the data, this is kind of what you look like. And so I've left sort of these cells blank so people can fill them in if they want to have their own chance of sort of visualizing how these different uncertainties translate over into actually what your model's predicting.